Hello, and welcome to How to Start a Program. My name is Anders. I work at a company called Zivid. We have a stand out in the food area, so if you want to drop by and say hi later, I'll probably be hanging around that one. I also run this C++ quiz site called cppquiz.org, so if you're into that kind of stuff, there will be a C++ quiz, a pub quiz at the party tonight, so please join, and if you're not into that kind of stuff, then please come to the party anyway and just skip the quiz. Before I start the talk, if there's anything unclear on the slides, please let me know so I can explain it during the talk. If you have questions more of the kind, I would like to know more about this kind of stuff, then please hold those to the end so that we can get through everything. And also a disclaimer, this is only about Linux. Everything here is Linux only, so if you're interested in Windows only or whatever, then there's still time to escape and go see Nico or Robert or something. Yes, how to start a program. So when I code, I tend to think a lot about the programming language. I think about my code, and the first thing my code meets is the compiler. So I tend to think quite a lot about the compiler. I get wrong behavior or compiler errors or warnings, and I Google that stuff, and there's a lot of information because people think a lot about the compiler. And finally, my code compiles, and the next thing my code meets is the linker. And I tend to think a whole lot less about the linker. If you think about the linker often, I feel sorry for you, really. Something is not the way it should be. And it's often also harder to find information, and people don't talk about the linker so much. But then when the program has compiled, it's linked, I tend to think even less about what actually happens when I run the program. So I just run it in the terminal, or I double-click the icon or whatever, and it just starts. But I recently had to find out more about it, and it's pretty fascinating stuff. And yeah, that's what the talk is about. So what kind of things need to happen for a program to start? This is engaging the audience. What's suggestions? What do you have to do to start a program? Yeah, you have to load your program. So I have some points here. Maybe you have to start a process. Maybe, maybe not. You definitely have to load the program into memory. So the code and maybe there's some data you need to load in. Maybe you have to initialize some data. So what kind of data would you have to initialize when the program starts? Yeah, so your static, your globals, your variables with static storage duration, you have to initialize as part of program startup, because they live for the entirety of the program. So yeah, globals, not your stack and heap variables, of course, because you call a function, the stack grows, and there's your variable. You call new, and you get some stuff on the heap, or whatever. But your globals have to be initialized somehow. And a lot of us, we have to actually find and load some shared objects somewhere. So dynamic libraries, shared objects, whatever you want to call them, DSOs. And then we need to get to main somehow, right? So when the program starts, we tend to think of it starts at main, but how do you get to main in the first place? And related to all of this is what happens really when the program exits. So that's kind of related to the startup thing. So I'll touch briefly on that as well. Before we talk about how to start a program, it's useful to think about what a program even is. And a program is just a bunch of ones and zeros. That's what we tend to say. But that's, of course, has some meaning. So these ones and zeros, there are just a long list of instructions for the CPU. And these instructions are very basic things. It's like, put these bytes into this register. Put that register onto the stack. Add these two values. It's very simple stuff, really. So no matter if you do fancy template meta programming or coroutines or what have you, it's just simple instructions going one after the other on the CPU, at least conceptually. I'll just need to adjust a quick thing here. There we go. Yeah, so here's a short program I will be using in this talk to demonstrate all of the things that we'll look at. So it's a simple program to compute the answer to life, the universe, and everything. So we just start with, we have some initial estimate of 40 and we figure out, well, that's not entirely correct, so we need to add 2 to that estimate, and then we have our answer, and we return that answer from main, so that's going to be the exit code from this program. And then we just compile and link that into a program called compute, and then we want to look at this compute program. So what does it look like on the inside? And on the inside of compute is this long list of machine code instructions that are going to be run on the CPU. And the most useful way to look at those is to look at the assembly, because every CPU instruction has a corresponding assembly instruction, so that's kind of the language we have to look at this stuff. So there's going to be some assembly in this talk. You don't need to know any assembly from before. The details are not really important, and I'm going to explain everything if it is important. If you're interested in getting into this kind of assembly code, then I have a talk from a couple of years ago at this conference called Just Enough Assembly for Compiler Explorer, which I'll have a link to at the end. So we want to look at the assembly, and then there's a tool called objdump, which will allow us to look at what's inside of our binary. We give it -d to disassemble and -C to demangle any C++ names. So we get the nice C++ names and not this weird mangled names. And we do -m intel to use the Intel assembly syntax, which is, I think, most commonly used these days. It's the default on Compiler Explorer and what I find most readable. And then objdump is going to show us the content. And the output is long. But here's some of it. Here's disassembly of section .text. And .text is where all your code goes. So there are a bunch of sections in here, but the .text section is where the code went. And I've redacted some stuff here, and then you have the addresses to the left, and then the assembly instructions. So at address 1129, we have the main function. So there's 1128 other bytes of stuff before, but here's where our main ended up. And main is just a long list of instructions. So I'm not going to go into what they do, but like at 1129, there's this nbr64, and there's some stack management stuff going on. And then finally, we get to this line, which actually comes from our program. So this has this value 0x28. That's our value 40 in hex. And it just says, well, put that into memory somewhere. And then we put that memory into some register, and then we add 2 to that register. So the point is, these are very simple things. So the CPU has an instruction pointer, which was then initially pointing over here. And then it just bumps the instruction pointer to the next one, execute the instruction, bump, execute, bump, all the way through the program. And that's really all the CPU can do. So it just goes like this through the entire function. The full output of objdump actually also includes the actual bytes. So these are the actual bytes that are in your binary on the disk. If you were to hex dump it, these are the bytes you would see. And these are the actual bytes that will be loaded into memory. Right, so you can actually see the bytes of your program. Yes, so instructions are simple, and they just get executed one after the other. But I've done a little refactoring here. So I extracted a function to compute this estimate answer, or to compute the initial estimate. So it's just called estimate answer. It returns 40. And we have to get here somewhere. And there's a group of instructions that I was going to say are a bit special, but they're not really special. They just also modify some data somewhere. So they can just change a register. It's just a set of instructions that happen to be able to change the instruction pointer itself. So the instruction pointer is just going like this, and then there's an instruction saying, actually write these other bytes into the instruction pointer, and suddenly it's pointing over here instead. And that's useful if you want to jump somewhere, you want to do some conditional stuff, you want to call a function, whatever like that. So we compile, link, and objdump this again. We look at the text section. And now we have 2 functions in the text section. So we have this new estimate answer function, and we have the main function itself. And all we can do is still like this execute next thing. So how do you get from main to estimate answer? Well, here's something that looks relevant. There's a call estimate answer. But that's just the objdump output. What's actually happening in the binary here is these bytes here. So E8 is the call opcode, and then E0FFFFF, that's -1b. So the only thing the CPU gets told, because the CPU doesn't know about function names or anything, the CPU just gets told, please take -1b, and call -1b, that's basically just going, please subtract 1b from the instruction pointer. And the instruction pointer is pointing here at the next instruction, and then we just subtract 1b, and suddenly we are at the first instruction of estimate answer. So then we're here, and then we just keep like execute next, all the way through that function. That's really all that happens on the CPU, kind of. But I did one more refactoring. I figured, well, this adjustment, we can't just have it as a local variable. Let's extract a global, because we love globals, right? So we have this global, this global adjustment value to 2. So first we call the estimate answer function to get the estimate, and then we can get this adjustment from this global. And neither of these are good refactorings, of course, but it's just to demonstrate some stuff. So if we compile, link, and dump it again, here's the disassembly of main. We still have the call to estimate answer, just like before. Then we have to get at this adjustment somewhere. So that's how we do that. What it does here, it's very similar. So it's using this offset. So for the call, it was just saying, like, -1b from here is where the function is. It's doing exactly the same here. So RIP is the instruction pointer. And then we say, well, 2EBE hex from here is where I'm going to find this adjustment. And then objjump is just nice enough to say, well, that's going to compute to 4010. And it also says, well, I can look at the symbol table, and I happen to know that 4010 is where you find the adjustment variable. So down here in the data section, which is a new section, so the .text section is where all the code goes, and then there's a .data section where some of our globals go. Down here we find our value 2. And objjump is again trying to be helpful, because it's a very helpful program. It tries to disassemble that data, and that of course makes no sense. It's a value 2. It just happens to disassemble to this stuff. So just ignore that part when you're looking at data in objjump. Yeah, so in the data section, that's only for your globals, for anything that's like visible to the entire program. So you don't have your stack or heap variables or anything in here. It's just for the globals. And this is basically all the CPU can do. Now you know how to call functions and how to get at this global data. But how do you get to main in the first place? Like, so far we've just been seeing, like, how can main get to other functions and do other stuff? But how do you get to main in the first place? On Linux, we are using the executable and linkable formats, ELF. And there's a nice tool called readelf that will let you inspect object files or shared objects, binary executables, whatever. Because the program isn't only code and data, there's a lot of metadata that is telling kernels and loaders and various programs some metadata that they need to do in order to run the program. So yeah, I give it W for wide output, which is always nice, and then H to look at the ELF headers. So the ELF headers are kind of like the main headers of this program, telling you the most important stuff. So it has like a magic number and a bunch of architecture stuff and ABI and whatnot. What we're interested in is this, the entry point address. And the linker is the one that wrote all of this stuff. And the linker does not know where the kernel is going to load your program. Like, it can be loaded anywhere in memory. So you can't say, here's the entry point, it's this address. What you can say is, hey kernel, load this wherever you like. And then the start of the program is then 1040 bytes into that memory that you loaded into memory. So this says entry point address 1040 hex. So kernel, please load stuff and point the instruction pointer over here, and then off you go, and then you run the program. So is 1040 where main is then? Let's objump our compute program again and look at the output. And at 1040 is not where main is. At 1040, we find a function called _start. And we didn't write this. This didn't come from our code. This comes from libc, and the linker just added this to our program. And it's doing a bunch of stuff that I'm just going to skip. A lot of like stack setup, like taking stuff from the stack and putting it into various places. And yeah, let's just skip that for now. Here it starts talking about main. But it doesn't say call main. It says LEA. And LEA is load effective address. So what it's doing, it's computing the address of main. And it's doing this in the exact same way that we call functions and access data and whatever. It's just saying, well, instruction pointer is currently pointing over here. D0 from here is where you'll find main. So it's just, again, doing this relative access address. And it's basically taking a function pointer to main and sticking it in a register. And this register here is going to be the first function argument for some function. And the next function is that function. So this is libc start main. So this is a function from libc which is responsible for starting your program. And this then takes the address of main, so it gets a function pointer to main, so that eventually it can call main. So the start is the start, it does some stuff, then it transfers control to libc start main, which can then do a lot more stuff. And at some point, you will actually get to main. So there's a lot of stuff going on here in start, a lot more stuff going on in libc start main. So let's see if we can make a minimal example. Yeah, so this is just to kind of show that there's no magic, kind of. It's all very simple. So this is the minimal program I could think of to return the value 42. It's pure assembly, it's 3 instructions, no C, no C++, no standard library, not even a main function. It's a very, very tiny program. We just say the start symbol is going to be an exported symbol from this object file, so you can find it again on the outside. Then it just says, well, now I'm going to output some stuff that needs to go in the .text section, which is where all the code goes. And then just a label saying, here's the start of the underscore start symbol. And then we're going to want to return 42. The way we're going to do that is to use a syscall. So the syscall is going to tell the kernel to exit with 42. And the exit syscall, which we're going to use, is syscall number 60. So we put 60 in RAX. And then the return value we want to return is 42, which is the answer to life, the universe, and everything. We put that in RDI. And then we just go syscall. And syscall then transfers control to the kernel. So now it's not like our program anymore. Now it's in the kernel, and the kernel can do its job, and we don't have to think about what's going on in there. The kernel is then going to say, well, someone called a syscall. Let's look in RAX. OK, so it's 60. OK, that's the exit handler. So I'll run the exit handler, and the exit handler is going to look, well, they're probably going to exit with some value. What's in RDI? 42. OK, and then the kernel can just exit the program. So this is then an entire program. So let's see if we compile, and this is just invoking the assembler and linking it into an executable called asmstart. And then we object dump this asmstart. Now this is now the entire text section of that program. So there is no main, no underscore start, no libc start main. Or yeah, there is an underscore start, but it's ours, right? And we can see it's only doing these 3 instructions. So the program now consists of these 3 instructions only, and we're able to return 42 from the program. And then all of this underscore start, libc start main, main, C, and C++ is just like adding stuff onto this. But this is all that happens. So when you do readelf on this one, it says entry point 401,000. So then the kernel is going to load this, set the instruction pointer to here, going to do this, and then we exit. And that's all that happens. And the rest is just like added onto that to provide niceness for us as programmers. And if you run that and then echo the exit code, we get 42. And even the underscore start symbol is not magic. It's just a symbol. So we could have called it let's go instead. So if you compare, it's just changing the name of the symbol. And you have to tell the linker that my start symbol is now underscore let's go. So there's a convention to just use the underscore start, but you can use any symbol that you like. So that's the most magical thing really that goes on. Otherwise, it's just entry points and assembly instructions. So this is a complete program that we just saw. And we will talk shortly about what happens when you add C and C++, libc and stuff into the mix. And then you get the underscore start, which eventually calls main. But how do you call underscore start? Okay, so we're kind of nesting down here. How do you get here? There's some stuff that goes on even before you get to underscore start. So now we're like so far only been talking about this program which computes this answer to the life, the universe, and everything. So like various iterations of a program to just return the value 42. So now we're going to put that to the side, and we're going to look at another program which is going to invoke this one. So we have this compute program which returns 42. Now another program is going to want to start that program somehow. And this is a really short program that starts another program. So it's just saying launching compute, which is the name of the computation program. And then we use the execve syscall. The execve syscall is just a function in the kernel kind of to launch another program. And if you've done this kind of stuff before, you might have used some wrapper, so like execve or execp or whatever they're called. But like they all boil down to this syscall. And it takes two arrays of char stars, one for command line arguments and one for environment variables. And we don't have any of those, so we just set both to an empty array. So then execve is going to run that program, and then eventually we're going to print compute exited with, and then the return value from execve. And we compile, link, and run this, and print the exit code. And what's this going to print? It prints launching compute, and then it echoes the exit code because of this echo exit code thing here. So it prints launching compute, and it never prints compute exited with, and then the return code. And that's because execve actually replaces the current program. So if you have a process, it's currently running this program. So yeah, I just call this program exec. So it runs this exec program, and then when you do the execve thing, the kernel is actually going to take that entire exec program and just chuck it out of the process and replace it entirely with this compute program. So execve in fact never returns out here. The only time execve returns is if it failed to launch this, then it sets result to -1, and then you can check or no if you remember to do that. So usually we don't want to replace the process. Like you're in your shell, you type ls, and then like when ls finishes, your shell is gone. So you want to preserve the currently running program, and then you have to do a fork. So fork will duplicate the process. So you call fork here, then you get 2 copies of this program. So if you're in your shell, now you have two copies of this. And then in this exec program, so we're running this program, and then after fork, we now have 2 processes running the same program. And then you have to figure out which one are you in. So the return value is 0 if you're in the child process. If you're in the parent process, you will get the process ID of the child. But the return value is 0, so we're in the child process. And then we can safely do the execve thing, because we're in the child process. We are actually supposed to be the compute program now. So now we can just replace ourselves with compute. And if not, then P is the process ID of the child, and we can continue in our old program that we wanted to keep running. So a full example would be something like this. It's full, except I skipped all the includes, and I skipped like all kinds of error handling just to be able to fit stuff on the slide. First we do fork. If we're the child process, we're going to sleep for a second, just because both processes are going to print to std out, so we just sleep for a second just so the output is nicer. And then we print launching compute. And then we do the execve exactly like we've seen a few times now. So now we're going to replace the program here with this compute program. And then, yeah, if that succeeds, then we're actually not going to print this line, right, like we saw before, because this program is just gone in this process. Yeah, and I also prefixed the output with a C, so we can recognize it's the child output later. If we're in the parent, we print waiting for child, and then we use wait, which is then going to block until a child process exits, and then we do some stuff to get the exit status and print the child returned whatever value. So if we compile, link, and run this, it says, like first, it does fork, and then child is going to sleep. So the parent has time to write waiting for child. Then it gets to wait, and it blocks. And now the child process can print launching compute. It's going to replace itself with the compute process, and then like never continue down here. And then when the child process exits, wait unblocks, and we can print that the child returned the value 42. And this is kind of what your shell does, right? When you type ls, it forks off something that can do that. So if we try to visualize this a bit, the fork call, say we have a fork exec process here, which is the program from the previous slide. We have a process running the fork exec program. It has process ID, for instance, 1, 2, 3. It has some metadata in here, which is stuff like the program name, your user ID, and stuff that the kernel needs to know. We have the text section, which is where the code for fork exec lives. And we have the data section where any globals for fork exec lives. And we have a heap and a stack and stuff like that. I've tried to kind of draw them as half full over here. Then we fork. And then we get another copy. And it's still running the fork exec program. It's just a new process with a new process ID running the same program. And then everything here has been copied. So behind the scenes, there's probably some copy on write and some reuse and stuff. But like from the perspective of the process, it's a new copy. So I can go and change global variables in the child without affecting the parent and so on. So it basically just duplicates the entire process, gives it a new name and a new process ID, and that's it. And maybe you have some pointers in here, right? You have some pointers from here to here, or some pointers going on. And anyone who's tried to copy a data structure which has like pointers to stuff inside knows that, well, then all your pointers are going to be wrong, because now they live in different memory. But this is virtual memory, right? So the address space of this process is exactly the same as this one. So all the addresses are still correct. The pointers are still correct. It's just backed by different physical memory that we don't see in user space. Yeah, so we copy the process, get a new process ID, duplicate the memory, but pointers are the same. And after having called fork, we call execve. Yes, so execve is a syscall. It's handled by the Linux kernel, and the kernel now has a lot of work to do. And the kernel has different handlers to do all of that work depending on what kind of program it is. But for, here it's the ELF, executable and linkable format, which is the most common one on Linux. And you have other handlers for like shell scripts and stuff, but we're not going to go into that. So when you call execve, then we still have the same process ID here in the child, but now we have new metadata set up. So that's like you have a new program name. Maybe you had like set UID set, so it has to update the user ID of the process, a bit of stuff like that. Yeah, then it can open the program file. So you can actually open the binary file called compute that we saw before. It can set up this new memory. It's not going to load anything in there yet, just like set up the memory. Yeah, and there's nothing in memory yet. Then we get a stack. So we get a little bit of stuff here in the stack. So we haven't gotten to start, we haven't gotten to main, we haven't even loaded the program from disk, but we already have some stack. And on that stack is stuff like the program name again, and environment variables, command line arguments, stuff like that goes on the stack even before the program is loaded. Yeah. Next, we finally load in the text and the data sections over here. So those finally get loaded. It has already opened the compute binary file. It maps in these things into memory, and then sets the instruction pointer to the entry point, which is the _start function that we saw. And then we return from execve. So all this is stuff that happens in the kernel when you call the execve. And the cool thing is, it was our the fork exec program called execve. We were still the old program. We call execve, we do all this stuff in the kernel, we return from execve back to user space. But now we're returning into a completely different program. Okay, so the process is still the same. It used to be the fork exec program, but when we return, everything has been replaced, and suddenly we are in the compute program instead, which is kind of cool, I think. So I've talked a lot about sections, so there's a brief mention of linking here. So imagine you have an object file called file1.o. Maybe it comes from file1.c or whatever. It has some text, some code, and some data. And we have another file2.o with some other text and some other data. And then the linker is going to link this into an executable. So it first takes all the text sections from all the object files and just stick them after another in one big text section in the new binary. It's not going to modify them or like split them up or anything. Like they're preserved in their entirety, just stick together in a larger text section. Then it takes the two data sections and make one combined data section, and so on for all the sections. And if you have any like relative calls up here, like jump minus b backwards, those are going to be still the same here, because it didn't change the layout of this. The linker only can like combine sections together. And if you have any relative data access here, like look at the adjustment value, which is like at some offset, well, that's going to be wrong now, because that distance has not been preserved. But the linker is the one that's writing out these sections. So the linker knows where it places things. So the linker can then go and just adjust these values as it's writing them out. It's decided the layout, and then we can just adjust these values to be correct. And that's also how, if you have a function called from here to down here, the compiler has no idea, right? What's the distance here going to be? The compiler doesn't know, so the compiler just leaves a note to the linker saying, can you please fill in the actual value when you're writing out the binary? That's handled by something called a relocation. And that was, I covered that in a talk here last year called From Program to Process, what happens after the compiler. So I'll have a link to that at the end as well, about how linking and relocations work. There's a bunch of other section types as well. So we have RO data for read-only globals, and BSS for any globals that are initialized to 0 or are uninitialized, because then they should be automatically initialized to 0. And we have symtab and dinsim for symbol tables and lots of stuff that we're not going to go over here. But if we look at this program again that we saw earlier, where we had the estimate answer function and the main function and this global data thing, then this one is going to go in the data section, like we saw, like it's global data, it goes in the data section, and all the code goes in the .text section. And then, if you want to look at these sections, we turn to readelf again. So readelf is the tool that will allow you to inspect binaries on Linux. And ELF is a quite complicated format. It has lots of metadata. So it has information about all the sections, where everything is, where everything's supposed to be loaded, and all sorts of stuff like this. So we can say readelf-w for wide output again, and then S for section headers. And readelf is then going to go, there are 37 section headers. So that means we have 37 different section types here. And we're not going to look at all of those, but here are some of these. So we have the .text, RO data, data, and BSS that we saw. So these are just information about where to find this stuff. So if you look at the headers here, it's going to say address, like where do I want this loaded? So the text section, I want that at 10A0 in memory, and it also happens to be at 10A0 offset in the file itself. So in the binary files, this is where you find the text section, and here is where I want you to load it in memory. But yeah, sections is what the linker thinks a lot about. It combines all these sections into combined sections. The kernel doesn't think about sections. The kernel thinks about segments. So it groups all like similar sections into a bigger segment. So the kernel doesn't have to load in 37 different sections. It has to just load a smaller set of segments, which are just combinations of these sections. So if you look at the program headers, this is the -L, then we can see the segments. And then it goes, there are 13 program headers. So it's taken all of these 37 sections and combined them down into only 13 segments. And there's a handy mapping here at the bottom where you can see that mapping. So for instance, segment number 3 has these sections in it, among others our text section. And then in segment number 5 we have all of these ones, and here's our data section. And then up here it's going to say what's the kernel supposed to do with all of these segments. And they're unfortunately not numbered, so we have to like count down here manually. But here we find the segments that we're interested in, number 3 and number 5. And again, it has these headers, so it says, well, here's where in the binary you find these segments, and here's where you want them to be loaded. So this is what the kernel goes doing. It looks at these program headers and take these segments and map them in. And if you see, I have to scroll a bit here. Oh, that was not scrolling. Yeah, here you can see some flags. So this segment is readable and executable because it contains your code. You want it has to be able to read the code and execute it, but you shouldn't be allowed to write to your code. You don't want the process to be able to like buffer overflow and write into your code. So this is where the text goes, and then our global data goes in the one which is RW, which is read and write but not execute. So you don't want to have like executable data in your program. If you want to visualize it a bit, so here's our sections. They're like down here at various offsets in the file. Here are the sections. They have some flags. And then you combine these into segments. So it's all the same data. We don't have like duplicated the sections and segments. It's just here's all the binary stuff in your executable. And sections and segments are just like pointers into like logical groupings of these things. So it's taken all of these sections here, combined it into one segment over here. And yeah, this one is read and execute. And here's some other stuff with our data, which is read, write. And the flags are a bit different. So here the flag for executable is X, and here is E for some reason. But this is what's going on. It's just writing out all of these sections, and then the segments are just logical views into that. So when we looked at our process earlier that had like the metadata, the text section, data section, stack, and heap, and so on, it would be more accurate to talk about segments. So it doesn't have just the text section. It has a data segment containing the text section and a segment containing the data section. So back to our program again. How do you initialize this value here? Like, whose job is it when the program starts to go and say adjustment equals 2 and put these other values into here, and here are some globals that has to have some other values? Who's doing that job of like going around and setting all those variables? Well, the object file has this value 2 in the data section that we just saw earlier. And the linker has then combined all the data sections into one big data section. And the kernel is then going to load the segment which contains the data section. And all of our code that accesses these globals has just addresses to like where to look for these globals. And then the kernel can just take the entire data segment and just chuck it into memory. And then suddenly all of these pointers are now pointing at the actual values that you want. So there's really never any active initialization. There's no one that has to go and like set these. They just get the correct value when that data is mapped into memory. But that's for a simple int, right? This is very simple C stuff with a constant expression with a fundamental type. It's very, very simple. You can just load the data. But I want to refactor my program yet again. I want to have an estimator class to get the estimate, because I want to be object-oriented or something. So I have this estimator class. It has this estimate public member, which the constructor initializes to 40. And then I have a global instance of this one. And then the question is, yeah, then you can see like when I'm going to compute this answer, I'm going to look at my global estimator and then inspect its estimate member. So here's my global, and I just check this member variable to get the estimate, which is 40, and then we add this other global, which is 2, and then we return the answer. So when is the estimator global initialized? Because now it has a constructor, so you can't just put some value in here. Maybe actually it could get like inline and stuff, but in general this constructor could be reading a config file, or it could like be connecting to a database or whatnot. It might not be something that's known at compile time, so it has to actually execute. So when is it initialized? It's actually so typically we just say it's going to be initialized before main, and that's kind of true. The standard only says it has to be initialized before the first ODR use, and ODR use is just standard use for actually being used for something. So before you actually use it, it has to be initialized. So like no later than down here, it has to have been initialized. But in practice, the way it's implemented is just do it before main, because then you're good. I think it's the same on Windows, at least on Linux, you just do everything before main. And it's actually initialized twice. And that's not an implementation detail, that's the standard saying, well, this global, it has a dynamic initializer. So it's first going to be statically initialized to 0, because this lives in some memory that gets zeroed out as the program starts. So first you get static initialization. It just fills in zeros, and then you can just hope that all your members actually, like 0 actually means something for that member type. And then you do the dynamic initialization, which is running the constructor. And you can in fact see here that this one doesn't live in the data section that we saw before. It lives in another section called BSS. And this is for everything that has explicitly been said equals 0 over your globals, or anything that you didn't give a value, because all your globals are automatically set to 0. Like, isn't that expensive to do it twice? It's not, because first of all, the BSS section doesn't actually exist in your binary. Like, you could have a global array of 1 megabyte. There's not 1 megabyte of zeros then in your binary. It's just a note saying, can you please allocate 1 megabyte of zeros over here? So it's cheap in the binary, and it's also cheap at runtime. You don't have to actually zero out that, because anytime you get a page from the operating system, it's already filled with zeros, so that you can't look at whatever memory the previous process was having. It could contain your password or whatever. So from C and C++'s perspective, it's kind of free to do the zero initialization. Yeah, for some reason, ObjJump isn't very fond of displaying this stuff. So the estimator lives here. It would look something like this. There's some other global here as well that I don't really know, but here's where it lives. It just, ObjJump doesn't want to show it for some reason. And then later, we have to do the dynamic initialization, so we have to actually run the constructor. And then, okay, how do you do that? Well, how do you get there? So what I did, I just ObjJump my compute program again and looked for the estimator constructor. And now here we have it. I found the constructor. So let's just search. Who's calling this? Oh, there's a call to this one. It's in something called static initialization and destruction 0. Okay, I just kept searching, like, who calls this one? Oh, here's a call in something called global sub-I estimator. So I just kept searching, and no one is calling this one. So we know that this global sub-I estimator is calling static initialization and destruction 0, which is calling our constructor, but no one is calling this one. So what's going on? There's another section called .init_array, and there are some suspicious-looking bytes down here. 7A11. If you look at where this function is, it's at 11.7a. And since we're on x86, it's like backwards, least significant byte first. So 11.7a is the address of this one. So down here in some sort of data section called init array, there's the address of this. So there's basically a function pointer down here. Yes, and there's also some other function pointer to some other thing that's probably coming from like some C or C++ stuff. The important thing is that we have a function pointer to whatever calls our constructor. So then someone can look at those function pointers at some point. Yeah, and what's going to happen then is the linker is going to find an init array in our object file and in some other object files, going to combine them together into one big init array, and then suddenly you have a nice data structure containing pointers to everything you need to do to initialize your program dynamically. So if we go back to our _start function that we saw before, this is the one we got from libc, not the custom one. It does all of this stuff, and then it calls libc start main. And then libc start main can then actually just iterate over all of these function pointers, and that's how you can initialize your stuff. So let's load our compute program up in GDB, put a breakpoint in the constructor, run the program, and then it breaks at the beginning of the constructor. If we then print the backtrace, we can see it started here in _start, as we saw. Then it went into libc start main, and here's like our chain of 3 functions that we found in overdump. So this call init is then the one that is responsible for iterating all of these over all of these function pointers and calling these sorts of chains from all the object files. And now we're at the breakpoint is at the beginning of the constructor, so the constructor hasn't run yet. So we talked about first static initialization to 0, then dynamic initialization. So dynamic initialization is just about to start. So if we print now this member of the global, it's 0. And that's not some implementation detail or some luck or something. That's actually the standard says it's going to get statically initialized to 0. And finish means just finish running the current function. So it finishes the constructor, and now we can print the estimate, and it prints 40. So yeah, there's an issue with reveal.js when this screen has a different aspect ratio than this one. But I promise this one says exactly the same as this line here, except it says 2 instead, no, 40 instead of 0. So we had our linking illustration earlier with the text and data section, where it combines the 2 text sections into one and the 2 data sections. We can do the same exercise now. So we have one object file with our estimator constructor and these 2 other ones that call it. And then the init array has this address of global sub-I estimator. So we have the function pointer to here, which is going to call this, which is going to call this. And we have another object file with some other global, and we have another global sub-I, other global. So it's another function pointer, so we can call this, which calls this, which calls this. And then we're going to need the _start function from libc. And the linker then takes all of these code .text sections, combine them into one big section. And actually, these 2 are called the same. So the 2 objects with the same name, and apparently that's fine since no one's actually going to use it for anything. Yeah, and then it takes these 2 sets of function pointers and combines them into this one big common list of all the function pointers that this binary is going to require you to run at startup. And this is kind of a hint at why we have the static initialization order fiasco, right? We don't know the order of when our globals are going to be initialized. And that's like, well, you don't know what the linker is going to do. Like if you pass these object files in one order, maybe they get like in the same order, or like who knows. So you can't know the order of global initialization. But yeah, we have the static initialization order fiasco, so it doesn't try to guarantee it anyway, so like we don't care. So yeah, then start is going to call libc start main, and then libc start main is going to do like for all of this init array thing over here to just call all the dynamic initialization. Yeah, so now let's have a quick look at program exit, because that's very related to startup. Like you start the program and then you exit it, and maybe some of the reverse things have to happen. What do you have to do to exit the program? What do you have to do with this global int? Nothing, right? You just stop using the memory, and it's like there's no work you have to do to just not use an int. But if I add a destructor to my global object here, then the destructor actually has to get called at program exit. And we saw how it calls all the constructor by just chucking function pointers in memory. Why can't we do that for destructors? What prevents us from just doing the same trick and like put function pointers to all the destructors somewhere? And at program startup, you have to call all the constructors. But you're only supposed to destroy objects that were actually constructed. So if any of your global constructors threw an exception, you can't go and then call the destructor on that object. So you have to like keep track of somehow which objects were actually constructed. And even if we have the static initialization order fiasco, we do have one guarantee that in some order you're going to initialize your globals, and then they're going to get destructed in the reverse order of that. So you don't know which order it is, you just know it's at least going to be the reverse of the initialization. So we can't just have like an array of function pointers. But if we look at objump again, we have this function here called static initialization and destruction 0. It says and destruction. So there's something going on here with destruction as well. So it's going to call the constructor, and then only if this one actually returns. Not if it throws, but if it actually returns as it should, then we can start setting up some destructor stuff. So these instructions are only going to get executed if it didn't throw. And it's doing something with the DSO handle. Let's ignore that. And what's interesting most here is it's taking LEA, load effective address. It's taking the address of the estimator global. So where's the instance? Where is this variable living in memory? And then it loads the effective address of the estimator destructor. So where's the instance that we want to call the destructor on, and where's the destructor that we want to run? And then it puts those in as some arguments to CXA at exit, which just registers all of this stuff somewhere. So presumably this is going to take then the instance pointer and the function pointer to the destructor, put it onto some sort of LIFO structure. So we have kind of a stack somewhere that at exit you can then like pop off things in the same order they were created, but only if they were actually created, not if there was an exception. So if we load our compute program into GDB again, break in the destructor, run it, and it breaks there, we look at the backtrace. And this is super annoying, and I can't fix it on the fly, I think. Yeah, but you can barely see it. Like, you can see libc start main here. So under here it says underscore start. So we're still in underscore start when the program is exiting. We're still in underscore start. We're still in libc start main. And then we're in this run exit handlers, which is then iterating somehow, like just popping off all the stuff from this stack, and then calling the destructor. So that's the entire thing. Like everything goes on in start. Yeah, that's how you get to initialize your stuff, how to call main. Unless you have dynamic shared objects, right? Dynamic libraries, SOs, DLLs on Windows. That's going to complicate stuff a lot. So now we know if you have a statically linked main, we know actually everything that's going on. But what's going on with this stuff? What's in an SO file? What's in a dynamic shared object? There's some code. There's some data. There might be globals with constructors and destructors. Well, the SO file has to get loaded into memory. This is very similar to executables. A shared object is extremely similar to an executable. It's basically the same thing, except it doesn't have main, kind of. And it's not at all similar to static libraries. So a static library is just a bucket of object files. They haven't been linked yet or anything. A dynamic shared object, like it's already been linked, everything is ready, it's one binary, and it's very similar to an executable. So there's only 6 minutes left of the talk. How are we going to learn everything about shared objects in 6 minutes? And that turns out actually to not be a problem. I introduce a new dynamic library here. I want to take this adjustment value. I don't want to have this here. I want it in a shared object, so we can share it among all our programs and make it like even globaler than it was. So I have this exactly the same as estimator here. It's just an adjustment member. And I just declare it, and we have a dynamic.cpp just for the definition. And then this turns into the shared object, and this turns into our binary as before. And then we slightly modify our binary to include the header. And then down here, instead of using the, we used to have this adjustment equals 2 on line here. So this is now instead getting it here from this adjustments global in the shared object. And then the same question is like, how do you run the adjuster constructor? How do you do like all the stuff we just did for the main function? So if you run objdump on your shared object, you find the constructor. Let's search for that. Well, here's a call. It's in something called static initialization and destruction 0. Well, who calls that? Well, here's a call. It's in global sub-I dynamic. Who calls that? No one. But there's a section here called .init array where we have some suspicious looking bytes. So 11.4c, that's this one. So this is exactly the same as the executable. Right? There's just a bunch of function pointers you have to iterate over, and then all the stuff we saw for binaries, for executables, is the same for this shared object. Just one question is like, who iterates over these things? Right? When we saw that the libc start main iterates over the initialization functions in your executable, but who does that for the shared object? And who loads the shared object? Is it the kernel? The kernel loaded our executable. Is it the kernel who loads the shared object? Because all of the same work has to be done, just slightly differently. So if you look at readelf again for our compute program, we can see it's requesting program interpreter ldlinux.so. And this is the dynamic linker and loader on Linux. And I'm going to skip this slide here. But yeah, so what is it requesting it for? What does it mean to request this? It means that I have linked against something dynamic. So there's some dynamic initialization going on. And that's the responsibility of ldlinux.so. And it's not the responsibility of the kernel. So if you want to run through a full example, you want to start our compute program which uses this libdynamic.so. Someone has called execve to even start compute. So we're in the kernel. The kernel is doing execve. The kernel is now about to replace the previous program with this new program in our process. It's going to read the headers like we saw. Now this is just repetition. We're reading all the headers from the compute binary, pair the stack, we load the program into memory, these segments. We then also load the loader. So now the kernel has loaded our main program, and it's also gone and loaded the loader. And then the kernel sets the instruction pointer not to the start that we have seen so many times in our program. It sets the instruction pointer to the _start inside the loader itself. That one also has a start. So this is kind of an executable, so to speak, shared object. It has a start function. Then, yeah, we return from execve, like we saw before, but now we're not returning into our program. We're returning into LDSO itself. LDSO itself has its own version of _start. It now has to do a lot of work according to a long list of complicated rules to figure out which libdynamic.so am I actually supposed to load here. And it's going to load it. It's going to update the global offset table, which is just like a table of pointers to all the globals in various shared objects, so that they can all find global data from each other. This was like half an hour in last year's talk, so I'm not going to go into the details. But then ldlinux.so is responsible for iterating over this initialization stuff in the shared object. So the kernel has called into Linux ldlinux.so, which is then initializing the shared object. So then it has to call into the shared object. So now the loader calls into the shared object and finally calls all of the initialization stuff in our dynamic library. And when that's done, we're back into the loader, and now the loader can jump to _start in our actual program. So now we're in here. Now we're in the _start that we've seen so many times. It goes like libc start main and all of that, and calls all our initialization stuff, which then calls, it's off the screen, it then calls the estimator constructor, and then finally it gets to main. So just imagine it says estimator constructor here, and then it says main below that. And that's the entire story. And there was really not much to learn about shared objects because they are very similar to executables. And that's it. Thank you for coming. These are links to the assembly talk and the linker talk. And yeah, you can find me on Twitter at these accounts if you want to have a chat, or I'll probably be at the Civit booth in most of the breaks as well. I think we're exactly on time. So if you have any very cool questions, let's do a few. If not, we can just chat after. Thank you.